Thank you for your kind introduction. So hello, I'm Hirotoshi Hirai. I'm leading quantum computing researches for material applications in Toyota Central Research and Development Laboratories. So nowadays, we can hear people saying we should give up on the NISQ algorithms and prepare for FTQC. So that's right. I agreed, but partially. So NISQ algorithm is based on hybrid quantum classical computing. Where we have to repeat execution of quantum circuit and measurement to statistically obtain statistically obtain the expectation value of some observer. So it's a Pauli strings, and based on this output value, we update circuit parameter, and we have to repeat this cycle until the stop criteria is satisfied. So we have to repeat this cycle so many times because the convergence is rather slow, so because of Barren-Plateau problem. So it is difficult to claim superiority over classical method in terms of calculation speed. But however, we have explored any other way to utilize NISQ algorithm. So today, I'll introduce two use cases with practical quantum benefit in material development as a preliminary step to advantages. Those are use case. So in terms of from perspective other than computational speed. So one is quantum chemical calculations without specifying spin multiplicity, and the second one is quantum neural network models with generalization performance superior to classical models. So let me move to the first topic, quantum chemical calculations without specifying spin multiplicity. So in conventional classical calculations on classical computers, we have to specify spin multiplicity in advance before the computations. So we have to write down spin multiplicity in the input file for the computation. However, in some cases, stable spin state is difficult to identify. For example, stable spin state of metal atomic cluster are difficult to identify. But these materials are expected as next generation catalyst for hydrogen evolution generation and CO2 reductions. And these materials are very important for our business and carbon neutral society. So these are difficult because stable spin state depends on the number of atoms and atomic species. So this graph, left graph shows the spin multiplicity of chrome copper alloy clusters, and they have very complicated spin multiplicity depending number of copper atoms. And another reason is stable spin state changes during chemical reaction. So there is a crossover of spin state. So most stable state, the ground state changes during the chemical reactions. But in most cases, we are interested in the most stable state to estimate the reaction energy. But we have to conduct multiple computations to identify it. However, in other hand, in quantum computing, superposition of multiple spin state can be prepared and handled. So in VQE calculation, the computation will converge to the most stable state, so we can find the most stable spin state. And this is because some answers doesn't conserve spin state, and famous hardware efficient answers also doesn't conserve spin state and can be used for this task. So this graph shows the potential energy surface of platinum CO system, and energy depends on the platinum CO distance. And this solid line and dashed line show the energy for spin singlet state and triplet state. And these lines were computed with classical algorithms on classical computers. On the other hand, VQE computation, the most stable spin state can be obtained with a single calculation. So every time VQE converges to the most stable state, so we can find the most stable spin state with a single calculation. So this result was obtained with quantum circuit simulator. So we also conducted a real device demonstration. So we used IBM Canberra machine, and this left graph shows the potential energy difference from the exact value, and the right-hand graph shows spin value, and this graph shows a 2-point platinum carbon CO distance. And for energy computation, we used 5,000 shots for each Pauli group, but we couldn't get accuracy within chemical accuracy. Chemical accuracy is criteria for industrial application of quantum chemistry computations. So we need more huge number of shots to calculate energy with chemical accuracy. And noises on NISC device prevent us to get such accuracy. On the other hand, in spin value, for spin values, we use only 16 shots for each Pauli group, but we could specify the stable spin state. This is because spin has discrete value, and Pauli strings of spin operator is shorter than energy Hamiltonian. So spin state can be identified with very small number of shots, even with noises in NISC devices. So let me summarize the first topic. The ground state could be obtained with just a single calculation using a quantum computer without specifying spin multiplicity in advance. And spin state can be determined with reasonable accuracy, even with using NISC devices. So this feature is very useful in developing materials with high spin states, such as metal clusters, so for next generation catalyst. So please refer to this paper for more details. And it should be noted that this research is conducted with collaboration with QNASYS. So let me move to the next topic, quantum neural network. So quantum neural network model consists of 3 parts: encoder and ansatz and decoder. So encoder converts input data X to quantum state. It's called as a future map. And in ansatz, this quantum state is transformed unitarily with running parameter theta. And in decoder, expectation value of some observer is computed as output Y. So this model works as function Y with input X. So QNN model has attracted too much attention because tensor product structure of quantum circuit allows us handle exponentially large basis function for the number of qubits, and unitarity of quantum circuit serves as regularization to prevent overfitting. So it has been known that QNN has higher generalization performance than classical models, especially in small data problems. We also find it with a regression task for AutoMPG dataset. So in this dataset, we predict fuel efficiency, mile per gallon, based on the explanatory variables, including engine cylinders and a number of cylinders and engine displacement and vehicle weight and so on. So this graph shows R squared value for test data. So it means a generalization performance for each model. And this graph shows quantum neural network model outperform classical neural network with and without regularization. So this advantage is bigger in the smaller data problem. So this feature of QNN is very suited for materials informatics because as in typical MI problem, we build a machine learning model that predicts the physical properties of materials from experiment and or simulation data. And then we search for desired materials by quickly predicting physical property on a huge material database using this machine learning model. However, there are two major problems here. So the amount of data cannot be increased due to experimental or computational cost. And some property like a dynamical property is very difficult to obtain with experimental and simulations. So data should be very small size. And another one is depending on the experimental environment, so noise can easily appear in the data. So model is prone to overfitting. So high generalization performance is required for the MI task. So we think QNN is the best candidate for this task. So to demonstrate that, we made QNN model to predict melting point of metal oxide. So metal oxide, we use metal oxide for support catalyst for exhaust gas purification catalyst. And because temperature of exhaust gas is very high, so durability against the temperature is very important for us. So we collected 70 metal point data from literatures, and each material was identified in the materials project database, and the following 5 explanatory variables were obtained. Where we tested various QNN architectures, in encoder we used RY gate for the future map, where we tested different equations to convert input x to potential angle theta. And we also tested several entanglers in ansatz. And let me move to the next slide. Okay. At first, let me show the effect of encoder. So this graph shows errors for each model. The horizontal axis shows a number of parameters. So for QNN model, by increasing the circuit depth, we can increase the number of parameters. And in the case of classical neural network model, so by increasing the number of neurons, the number of parameters can be increased. And focusing on the classical neural network model, so with regularization, without regularization, this blue line shows solid blue line shows the result for test data, and dashed blue line shows the result for training data. So by increasing the parameter, the error can be reduced for training data, but errors for test data for unknown data increases. This is a typical overfitting tendency. On the other hand, QNN model, except the small region, show no overfitting tendency. But there are large differences between these QNN models. So this is because of encoding method. So we tested theta equal pi x and theta equal arctangent x. And in the theta equal pi x, the input value from input value x, the quantum state go around the Bloch sphere. In this case, z-axis projection is not unique. So immediately after the encoding, the observer power Z is not unique for this input. On the other hand, in the arctangent equation, we can encode X to uniquely the quantum state, because quantum state go around hemisphere, half of Bloch-sphere. So always Z-axis project can be unique. So immediately after the encoding, the observer is also unique, can be unique. So high performance model can be obtained by using an encoder with unique conversions. Okay, next I tried some encoder, entangler in ansatz. So we tested several entangler in ansatz, but surprisingly, too much complicated CNOT gate result in poor performance. But on the other hand, shallow ansatz with linear is sufficient to achieve the good performance. So clarify why we evaluated entanglement and expressibility of ansatz. So upper graph shows the entanglement entropy. So for the ansatz, so strong entanglement can be obtained with stronger entanglement entropy. And bottom graph shows expressibility. We evaluated KL divergence between fidelity of random parameter circuit and Hall random state. And we can see that a circuit with stronger entanglement has stronger expressibility. So this graph shows us circular hole, this complicated circuit results in very weak entanglement and results in poor expressibility. This is because existence of identical reduced circuit. So this complicated circuit reduced to this simple one. And so this tells us blindly applying CNOT gate doesn't make substantial actual entanglement stronger. Okay, finally, let me show the result of circuit width. So we can increase the number of qubit, and we can encode embedding input X redundantly or as a squared value. So in these wider circuit can show better performance, outperform the classical models, and a bit better performance can be obtained with squared embedding method. So increasing the number of qubits increases the dimension of the base function and can improve expressibility of the model. Okay, let me finalize the second topic, QNL models. We made QNL models to predict the melting point of metal oxide, and no overfitting was observed. And shallower depth ansatz could achieve sufficient expressibility using sufficiently entangled circuit. And the expressibility could be further improved by increasing the circuit width. So these findings suggest that QNN can be useful tool for MI. So we can replace existing regression model right now. So please refer this paper for more details. This is my conclusion, and thank you for your kind attention.